All right, so today we are week 4, lecture 7. Hi there. Did you get a request to evaluate the class for the? Please, could you do that now while we're doing it? While we're starting. That's why we're starting late. Thank you. All right. What we're going to do today is we're going to finish a calculation of what is called the Ginzburg criterion, which is going to enable us to understand when we see departures from regular mean field theory and need to start worrying about renormalization group type considerations. And that's going to bring us into worrying about coarse-grained descriptions of the system and how to improve our description to take into account spatial fluctuations. So let me just recap what we did last time. So last time we introduced the static susceptibility, and I proved it to you. And what we saw was that the susceptibility is actually related to the two-point correlation function of the fluctuations. So here's on the right panel is the two-point correlation function, and you can see that I've written it as the expectation value of delta SI and delta SJ. So delta SI is the fluctuation. It's the value of the spin in any configuration minus the average value. Then we multiply it by the same thing for spin J, which could be anywhere in the system. And then we take an ensemble or thermal average of the system. And if they're correlated, that means that if I look at this fluctuation over here, I look at the fluctuation over here, they look the same. They might be even anti-correlated, but they're still correlated. Then as I average over many different configurations, I'll keep getting the same number or something like the same number, and so I'll get a big number. On the other hand, if when this one is up, this one is down, and there's no real correlation between them, they're just randomly fluctuating, then when I take the thermal average, the average is all going to just give me 0. So this is a measure of how the fluctuation at site I and the fluctuation at site J are correlated. It's not a measure of the order parameter at the site. So when I talk about order parameter, I haven't formally introduced that term yet, but think of this as just being the magnetization per spin. In other words, this is the thing that as I go below the critical temperature starts to become non-zero. And we've seen that right from the first lecture. That's the thing that an example of what we'll call order parameter. So it's not the order parameter itself that's correlated, it's the fluctuations in the order parameter. Okay, so that's the first thing. And then what we proved was that the susceptibility is related to the integral of the correlation function. And we noted that the correlation function depends on a particular scale. It tells you how long, over what distance correlations extend. And so it turns out that at long distances, the correlation function decays exponentially. And because it decays exponentially at long distances, what that means is that the integral over here on the left-hand side is going to be convergent. But we also noted that near the phase transition temperature itself, the susceptibility actually starts to diverge, and we've already calculated that. And so we wanted to understand how is it possible for something to diverge as you go towards the critical temperature, whereas on the right-hand side is a quantity that is guaranteed to converge. And the answer to the question was that the correlation length itself diverges. And we calculated how it diverges, at least in mean field theory, by knowing the fact that if we know the left-hand side diverges as something to power -1, then the right-hand side, we can evaluate that, and we can see then how the correlation length, psi, must behave. And we found that it diverges as T minus TC to the -1/2 power. And then what we discussed at the end of the lecture was that what happens is that the small distance behavior of the correlation function is actually varying slowly, and to a leading approximation goes as a power law. And then what happens is as the correlation length grows to infinity, if you're measuring at a particular scale, what you start probing is no longer the large distance asymptotics of the correlation function, but the small distance asymptotics of the correlation function. And that's how you get a crossover from exponential decay of correlations to power law decay. So then we wanted to ask the question, well, how good is mean field theory? Does it work? We actually know that it doesn't work, at least below 4 dimensions. But now we want to try to understand, can we actually predict its limitations? And the answer to that is yes. And that was what we talked about at the end. So what we discussed at the end of the lecture was, what are we doing when we do mean field theory? And what you are essentially doing when you do mean field theory is you're replacing the instantaneous value of, say, a spin variable, in the case of spins or density or whatever it may be, you're replacing that by its average. So what we did when we derived mean field theory, when we did it in class, what we did, and now look over here on the left, was we took the interacting Hamiltonian, the product of SI, Sj, the term that makes the Hamiltonian impossible to write as the sum of terms, and therefore the partition function cannot be written as a product. And what we said was, well, let's just replace SI, Sj by SI times the average of Sj. That was the effective field that we introduced. And what that meant was that we could then solve the problem. So the fractional error that we are making in that approximation is just the average of SISJ, the true value, minus SISJ, our estimate of it, divided by SISJ, expectation of SISJ over here. So this is the fractional error, and I call that thing E. Now you look at that and you say, well, that numerator is in fact the 2-point correlation function. So we can then, and the denominator is just the magnetization per spin squared. So what we ended the lecture by expressing was the fact that this error estimate is basically the correlation function at the distance r divided by m squared. And the question is, how do we choose r? And the answer is, well, you could just say, well, r is just the range of interactions, but that's not a very good answer. So you could say range of interactions, but that's not a good answer. And the reason it's not a good answer is because we know that the range of interactions is just set by the microscopic physics. But the thing that actually grows when you go towards the phase transition is the correlation length. So it's correlations that grow. So the answer is range of interaction, nobody cares about. That's like, a few angstroms or something. But spin variables start to become highly correlated. And because they become highly correlated and not independent, that's what makes phase transitions hard to solve. So no, because the range is T independent, but it is the correlations that grow as T tends to TC. So because of that fact, the better way to measure R would be R should be some measure of the correlation length itself, which is then temperature dependent. So now we're tracking the length scale that characterizes what is the thing that makes it difficult to solve this problem. It's the correlation length. And if we're going to make it like that, we may as well make it an integral of that. So what we do, the next step is then we say, okay, well, let's write down, let's average over a correlation volume. So in other words, we're going to take our error estimate and write it as the integral, the ddr, over the volume of g of r, divided by the integral over a volume ddr, the magnetization. And I'll write magnetization as being site dependent, so something like that. And then how do we choose this volume? Well, we're going to choose this volume is equal to psi to the d, because within a correlation volume, correlation length, and therefore thus a volume, the degrees of freedom are highly correlated. And then beyond that, they're not. So we can think of then as V as being xi to the d. Now, that V being xi to the d, we can still evaluate this integral as if V is going to infinity, because beyond xi, there's only a small contribution to the integral. It's converging exponentially. So it just gives you a small number. So basically then what we can say is that E is the integral over the entire system of G of R. And then over the bottom, well, this is just going to be m squared dr over V is equal to xi to the d, and we're going to evaluate those because m is just a constant. We have to literally take that volume to be xi to the d. So now let's go and estimate this. And so what is the trick? So the trick is that we use the static susceptibility sum rule, and that means that the numerator is just, to a very good approximation, just kbTc times chi t, and so that will scale like kb times tc divided by absolute value of t to the power gamma, and because the susceptibility diverges as t goes towards tc, and gamma in mean field theory is equal to 1. Okay, so that's what the numerator is, and you can see the numerator is indeed getting big as t tends to tc. Now, when we look at the denominator of this thing, so the denominator is just xi, the volume, to the d, times m squared. And so xi goes like t to the minus nu. So this goes as t to the minus nu to the power d times t to the power 2 beta. So each m scales like m to the beta, goes like t to the beta as I get close to the critical point. The correlation length diverges as t to the minus nu. We know what the values of these things are in mean field theory. Beta mean field theory is equal to 1/2, and nu mean field theory is equal to 1/2 as well. So so then we can evaluate how our error estimate scales. So this implies that our error estimate averaged over the appropriate region of the correlation volume. So that basically scales, and I'm just putting in the t dependence here. So it scales as t to the minus 1 from the numerator times t to the power 1 minus d over 2 in the denominator. So notice here, over here, we have this factor of xi to the d that comes from this volume integral over here. And so I get xi to the power d, xi goes as t to the minus nu, and so I get a factor of t to the, with a dimension dependence in it. And so let's now write that down. So this then is equal to so not equal to, this scales, taking away the other factors, as t to the power minus 2 minus d over 2, like so. Yep, like so. So this is a very interesting equation. Okay, so what this says is that so the question that we're asking is, as t goes to 0, i.e. t goes to tc, what happens to our error estimator? That's the question we're asking. And remember, as we discussed at the end of last time, if the error, if E goes to 0 as T tends to TC, then that means that mean field theory is good. Because we've said we're going to make an approximation. We're going to calculate how good that approximation is within the theory that made us the approximation. And if the theory then predicts that the approximation is indeed good, then everything is great, everything is happy. So that's one answer. If E goes to, let's say, infinity, as T tends to TC, then that says that mean field theory is bad as we get close to the critical point. It means it ultimately breaks down. So now let's see, what did we predict? So you can see that for d less than 4, then E psi actually diverges to infinity. So for example, let's put in d equals 3, then you can see that E psi scales like t to the minus 2 minus 3 halves, which is t to the minus 1/2. And so as t goes to 0, E goes to infinity, and so we have a miserable conclusion. But on the other hand, if d is greater than 4, then E psi will go as will go to 0 as t goes to 0. So example, if I say d equals 6, then E psi will go as t to the minus 2 minus 3, which is t to the plus 1, and so therefore goes to 0 as t goes to 0. And so what we've predicted is a remarkable conclusion. We've concluded that mean field theory breaks down below 4 dimensions, and this is why it's a very hard problem. Now this is also tells us another thing. So you might think that phase transitions is a problem with a small parameter, namely t, right? We have a small parameter, t minus tc over tc, that is definitely going to 0. It's a small parameter. So you would think, based on that, you would say, well, if I have a small parameter, I should be able to use perturbation theory. Okay, that's what you've been taught. Okay, you have small parameters in the problem. Once you have small parameters, you use perturbation theory, you're done. Okay, but we've just found that it's not like that. What we found is the answer is no. It is not a usable small parameter. Okay, that's what this calculation has shown us. Okay, it has shown us that even though this thing is getting small, actually the error that we make in doing perturbation theory is actually large and gets worse as we go towards TC. So later, I'm going to show you. We will use dimensional analysis on field theory description to see why it is not usable. This was the big surprise. People thought back in the, well, why this problem took 50 years to solve, after Landau came up with his sort of description of phase transitions that I'm about to explain to you now. It seemed like, well, this should be an easy problem to solve. It turned out to be impossible. Okay, and I'm going to show you why it's impossible, and indeed how we solve that using the renormalization group. So that's the conclusion, and let me just make a comment about notation. So our comment is that we define D equals 4 as the upper critical dimension. So for D greater than D upper critical, which is in this case 4, we can mean field theory is okay. And we had another dimension. We have, reminder that the lower critical dimension D lower critical for D, if D is greater than D lower critical, which in this case is equal to 1, that means that you can have a phase transition at non-zero temperature. More precisely, that you can have long range order, which we'll talk about what that means in a bit. So we now have an upper critical dimension and a lower critical dimension. So now I want to talk about then space, because up to now we've sort of really avoided discussing space in any significant way, and so now I want to remedy that. So let's just finish this section by writing a summary. So here's the summary. So I'm going to draw a temperature axis here along the horizontal axis like so, and then I'm going to put TC here, and then I'm going to define a new temperature, which I'm going to call TG. I guess I'll do one down here. So this is well. This is TC plus TG. This is TC minus TG. And so basically our picture that I've just told you is this, in this region here, in that region over there, mean field theory is okay. And then in the central region, mean field theory breaks down. And of course, we need to know what replaces it. And this region is called the critical region. And it's a hard problem because there's no small parameter. All right, so now I want to now talk about a different level of description. So the next topic is I want to look at how to construct a coarse-grained description of the system. So in our early lectures, we talked about different levels of description. So what I want to talk about is I want to look at scales intermediate between the microscopic and macroscopic. So let me draw a picture just so that you get the idea, and then we're going to write down some equations. So here is a picture. So let's suppose I'm going to just draw this in one dimension, but this picture I want you to think of as being in d dimensions. So I've got my spatial degrees of freedom, and then I could have at the microscopic level, I've got my spins pointing. I'm just drawing some random configuration, something like this. So this is our microscopic configuration. I've got my spins. Then I might say, well, actually what I want to look at is the thermodynamic level of description. So here is my space. I'm going to look at the thermodynamic level. In the thermodynamic, I don't really have any variables, any spatial resolution at all. So I just simply measure the magnetization, and M is just a constant independent of space. So that's the thermodynamic one that we've been working at up to now. But now you might say, well, we can make an intermediate level description. So it's intermediate between those. I'll call it a coarse-grained description. And what we might say is, well, what I want to do really is I don't want to have a description of the system in terms of spin here is up and down and up and down and so on. I like doing calculus. Okay, and this function that I have for the magnetization in thermodynamics is just a constant line. If I were to say, well, let's suppose I were to look at the microscopic configuration, but I took off my glasses, so everything was fuzzy. Okay, then what I would see is not the spins. I would just see some vague thing fluctuating in space in a continuous fashion. So I would see something that maybe looks something like this. Something like that. So this would be a coarse-grained description, and the variables that I'm plotting here are the spin variables, and then what would be this variable? Well, this variable would be, say, the magnetization as a function of distance. You could call it that. I might give it a name. I might call it psi of r more generally. But in order to get something smooth like that, I can't just sort of wave my hands and wish for it. How would I get that? Well, what I would do is if I take off my glasses and look at my microscopic spin configuration, what I'm seeing is I don't have very good resolution. So I'm looking at a blurry image. So how big is the blur? Well, it depends on how bad my eyes are, right? So the blur in this image has a length scale associated with it. And that length scale is the scale that I'm using to coarse grain. So what you might say is, well, let's suppose I coarse grain over this region. Let me call this region of size lambda. So I'm sort of taking those variables, I sort of blur them together, and that then gives me, say, this point over here. And then I take these variables, and now I move it this blur along to just a different position, and then this blur gives me this point over here, and so on. So basically what I have is I have a sliding window of blur at scale lambda that moves along the R axis or R dimensions. And then by averaging, really what I'm doing is I'm taking my SI, I'm multiplying them by some kernel that depends on Ri minus Rj. It could be some Gaussian kernel or something like this. I integrate over Ri. This kernel might be something like e to the minus Ri minus Rj squared over some length scale lambda squared, something like that. So I've got this blur, this Gaussian kernel that slides along, averages the things together by doing an integral, and then that's how I can generate this smoothly varying function. So we think of this as being so we generated a coarse-grained description by writing that M of R is I take the spin values at various sites SI. I multiply. Well, let me write it like this. I multiply it by Ri minus Rj. And integrate over Ri over Rj, excuse me, like so, and then this thing is divided by lambda squared over 2, and so this then is a coarse-grained variable, and this coarse-grained variable continuously depends on space. So really, I can think of this as you tell me what R is. I'm going to write it. Going to improve this. You tell me what R is, and what I do is I apologize for this. I'm going to just write this a little bit better. So I choose R minus Rj squared over 2 lambda squared, normalized by 2 pi lambda squared to the d over 2, and then this is a spin j, and so what I'm doing is I'm averaging the spins around the site R. So you tell me what R value you want. That R value is in here. I then average over the spins at site J, distance Rj away from that, take that average, and then that's going to give me a spin variable. And now this is a coarse-grained variable that depends on space. Now, because it's coarse-grained, it really depends on the coarse-graining scale as well. So because I've got this lambda in here, that means that this M depends on lambda as well. So when I write this lambda, I really should be writing it like this, telling me what is the coarse-graining scale. So that's the idea of a coarse-grained variable. Okay. Now, the question that you want to ask, so I can always do that. And so now the question is, what is the probability distribution for m lambda of R? And we're going to have to work that out. Now, what we know is for so this is analogous to saying what is the probability distribution function for the microscopic spin variables? Well, we know the answer to that. That's the Boltzmann distribution. So the probability of finding the system in some configuration SI is equal to 1 over the partition function e to the minus beta times the Hamiltonian of the spins. So that's true for the SIs, and so we want to know what it is for the M of R, and so we're going to write it in the following way. By analogy, we're going to say, well, we're going to write that the probability of finding the system with a coarse-grained order parameter M of R is going to be 1 over some partition function, a normalization factor of a new variable. So we have the Hamiltonian that tells you the distribution for the microscopic spins. So we're going to write the effective Hamiltonian for the coarse-grained order parameter. We're going to write that as L, and we're going to construct it. So what we're going to say is it's going to have this particular form. We're going to call L the Landau free energy. We might also use other terms. We might say it's the effective Hamiltonian. At scale lambda. Because what we've done to get there is we coarse-grained our microscopic degrees of freedom on a scale of lambda. And so we have the idea that the description of the system depends on the scale at which you look at it. So that's a definition. I haven't yet told you how to find that, but we are going to construct that. And so then what will this thing tell us? Well, so why useful? Well, if we could do this process precisely, then what we would have is a multi-level description of the system. So at the thermodynamic level, we have a description of the system like that. And this of course is the thermodynamic partition function. And F is the Helmholtz free energy. So that's our description of the system in thermodynamics. Then we have at the microscopic level over here, we have e to the minus beta times the Hamiltonian, which now depends on the microscopic variables. And we know that in order to get the partition function, what we do is we take the trace over these microscopic variables. And in the case of spin system, we know exactly how to do that. And so this is our microscopic lattice scale description of the system. So now we have this effective description at intermediate scales. So we know that this thing is equal to this. And then in the intermediate scales, we've proposed that there is some free energy. And let me just say it's m lambda of R times beta, like this. So that's our microscopic description. So we have a free energy that describes these long-range variables. And then what I have to do in order to get the partition function is I have to now take the trace over all possible values of m lambda of R. So let's just talk a little bit about that. So when we take the trace the trace over the SI, we know that that is equal to the sum of S1 is plus or minus 1, S2 is plus or minus 1, and so on all the way up to Sn is plus or minus 1. So this is basically, we sum over all possible microscopic spin configurations. So that's what we mean by that. Okay, so now let's ask ourselves, well, what do we mean by trace over m lambda of R? Well, what is this is going to be? Let's say it in words, and then later we'll talk about how to write it down in equations. So what we're saying is our description of the system, instead of being a bunch of plus and minus ones, a string of those, now we have a continuous function. And if we're going to sum over all the possible values of the plus or minus ones, now what we're going to do is sum over all possible continuous functions. So this is going to be a sum over all possible continuous functions m lambda of R. And why is the lambda important? If I said to you we're going to sum over all possible functions, you'd say, wow, that sounds a bit strange. But in fact, these functions are not arbitrary functions. Okay, so note m lambda of R is coarse-grained on the scale of lambda. That's how we constructed it. So because it's coarse-grained on the scale of lambda, what does that mean about its Fourier components?
It has to be multiple of lambda, like the period or something.
Well, it's not. Don't worry about the periodicity of it, but I want to know about. Remember, I still have the volume of the system.
Yeah.
So if I want to know what are the states of the system, they'll be quantized in each direction in terms of 2 pi over L times an integer. So that will still be true. Okay. So I can then take a Fourier transform, but what do we know about that Fourier transform if we've got a function coarse-grained on the scale of lambda?
The scale lambda will determine the frequency, like the size of the momentum space.
It will. That's true, but it won't define the quantization of it. Okay, so that's the same thing. This quantization scale will be set by the system size. Okay, 2 pi n over L, where L is the system size, not the coarse-graining scales. So suppose I take m lambda and I did its Fourier transform. Do you think it will have spectral weight, meaning non-zero Fourier components for all values of k? Frank?
It has a cutoff. Well, like if you coarse grain on a long scale, your wavelengths will necessarily be long scale, right?
Right.
And there'll be some k below or above which like you can't have any
Right.
wave vector.
Right. So basically, if you have any oscillations in your microscopic degrees of freedom on a scale that is smaller than lambda, those will all be washed out by the coarse graining. So this is coarse grained on the scale of lambda. And so what that means is that oscillations on spatial scales smaller than lambda will be averaged out. And so what that means then is that if I took m lambda and I took its Fourier transform, that thing will have no Fourier components or very few Fourier components for k greater than 2 pi over lambda. And so these functions will, these functions are not just random functions. They are random, but they also have structure. And so when we want to make a mathematical sense of what we mean by this sum over all possible continuous functions, what we're actually going to do is write this as in Fourier transform space, and write this as an integral over the Fourier transforms. So this thing here, this thing defines, this thing is called a functional integral. And we'll talk a bit more about it later, but roughly speaking, you can think of this as being take the product of over k less than 2 pi over lambda, in other words that, and then look at the product of dmk, and since the Fourier transforms are since the Fourier transforms are complex numbers, so this will be d real part of mk, d imaginary part of mk. And then we sum over k. And so roughly speaking, we're going to get a multi-dimensional integral in k space where we sum over Fourier components, but we only look at the long wavelength components. And that's important because we know that the physics here is all long wavelength physics, because the correlation length is going to infinity as we go closer to the critical point. So that's what we're going to see. Now, this intermediate level, this coarse-grained description, right. So this is the I want to just label this. This is the coarse-grained scale. So this coarse-grained description applies on scales microscopic lattice. Coarse graining scale should be bigger than that, and then the coarse graining scale should be less than the system size. There's our coarse graining scale, and then we know in this problem there is a correlation length. So near the critical point, we know that we have the correlation length scale as well. So we have our lambda, we have the correlation length, which is temperature dependent, and then we have the system size, like so. So what's going to happen is near the critical point, because lambda should be close to, or maybe a bit less than the correlation length, and we know that psi of t, this goes as t minus tc over tc to the minus gamma, as t tends to tc. We know that this coarse graining condition is automatically satisfied. And not only is it easy to satisfy, but it turns out that the results, at least in this range, are independent of what we choose to be independent of lambda. Okay. just like you would expect. You average a bunch of variables, the results very quickly converge. They shouldn't depend strongly on lambda. So I said independent of lambda. What I really should say is weakly dependent. Okay. So that's the story. Now the question is, well, okay, this is all great, but how do I construct this Landau free energy? So the next question. How do we construct this coarse-grained order parameter? And not the coarse-grained order parameter, but the effective Hamiltonian for it. And the answer is, you might surprise you. So the answer is it's virtually impossible. Okay, so you think, wait, I just spent 20 minutes explaining how great this thing is, and I've told you that, hey, never mind, we actually don't know how to calculate it. So first thing is it's virtually impossible. The second thing is, but it doesn't matter. Okay. Okay, so it doesn't matter. And why doesn't it matter? Well, we can understand the main features of this just from analyticity and symmetry. Okay, so it doesn't matter because we can construct it just using analyticity and symmetry. And we've already seen how to do that, right? You already in homework 1, you calculated the Helmholtz free energy near a critical point using our 10-second theory, and you saw that it had to be an even function of the magnetization. So that was how we used symmetry. How do we use analyticity? Well, the coarse graining is done over a finite region of space. We're sliding this window along like this. That's what we're doing by coarse graining. When we're coarse graining, we're summing over a finite number of degrees of freedom. Because we're summing over a finite number of degrees of freedom, everything we calculate must be analytic. Because if I just add up a bunch of finite number of variables, I'm bound to get an analytic function. So the analyticity comes in. So that's where the analyticity comes in, and the symmetry we've already seen where it comes from. So that's the first thing. So you can say, okay, well, I can get the functional form maybe, and we'll see how to do that. But how about all the coefficients in there? There's going to be coefficients in the free energy. Why don't I care about those? The reason I don't care about those is because in order to compute critical phenomena properties using the normalization group, what we're going to see is that any coefficients in our effective Hamiltonian are also going to be functions of scale. And as I do the normalization group calculations, what I'm going to be doing is looking at the effective scale, looking at the effective Hamiltonian at different scales. And as I change the scale, the coefficients are all going to change. Eventually, they will go to some fixed point value, some constant value, and I don't care what that value is, but once it goes to that value, then it enables me to compute the coefficients. Remember, we've seen that the exponents and the scaling functions are universal, and we're going to see how that comes out here. So it's also the case. So symmetry. So that's imposed by the Hamiltonian, and then the construction are all coefficients in powers of m lambda of r in this Landau free energy, these coefficients, they are functions of scale. And eventually converge to fixed values. And that's what gives you, in fact, the universality. So I haven't proved that to you yet. We're going to see that later, because we're going to be starting the normalization group very, very soon. And so we'll actually literally go and do that. So let's then now try.
So we don't have to worry about the exponent. We just have to worry about the coefficient.
We construct the exponents. I'm going to come to that right now. So the coefficients in the Landau free energy, we're going to compute just by symmetry. I mean the exponents, the power series expansion, and then the coefficients we don't care about. And we'll see why, because they flow, meaning as I change the scale, they'll flow. And what the normalization group is an iterative procedure to change our description of the system at different scales. So all of that I will explain to you. Okay, so now here is the strategy for how we compute this. So step one, you kind of have already done. Step one is we're going to construct our mean field theory for a homogeneous system. So and how do we do that? Well, we can ask ourselves the following question: what free energy would generate the mean field equation of state near the critical point? So you work that out in homework 1, and I'll just remind you of that in a few minutes. Okay, so that we know how to do. Okay, then step 2. We're going to add spatial variation. And we're going to add spatial variation in a way that is only for long distances, because those are the only things that matters. And so that means for small wave numbers, k going to 0. So we're going to look at those things, and then of course we will combine them. Okay, so let's do step 1 first. So let's remind ourselves what is our equation of state. So our equation of state is h over kbt is equal to mt plus m cubed plus higher order terms. Okay, so you've derived that now. We've derived it in class. We derived that a couple of lectures ago. So I'm just, and maybe there's some coefficients in there, like a factor of a third or something like this. So that's what you get. So you could say, well, what free energy would generate this? And so I could say, well, let's put out, I have a free energy which I'll call L of H and M. So what I would say is, well, if I take that free energy and differentiate it with respect to M and set it equal to 0, that should give me the equation of state. And so you can see that what I get then is that L of M, H, and then T is equal to, let's call it L naught of T and H, and then minus MH, excuse me, over KT, and then I would have plus 1/2 T times M squared plus M to the 4th over 4. So that's the free energy that, if I differentiated it with respect to M, would give me the equation of state. Okay, so that's the first thing. All right, now let's add space. So I'm going to do this. I'm going to do this in a simple way. So and then I'm going to justify it microscopically. So step 2 is if we add space, we want to look at long distances. So then you could ask the following question: well, let's think of it like, let me think of it like this. Here's how I want to say it. So up to now we have L is a function of M, and we've written it in the form of some L naught minus MH plus 1/2 T M squared plus 1/4 M to the 4th. So now we want to make M go to M as a function of R, okay? So you could just say, well, then L as a function of M of R, and I'm suppressing the coarse graining scale just to make it easier. You might say is that's, well, the integral dr of M of R, maybe a spatial dependent field H of R, plus 1/2 T M of R squared plus 1/4 M of R to the 4th. So you might say it should be something like that. Well, that's not quite right. Okay, that just says, okay, my M is now a function of R, but we also expect that there should be a term in here that reflects spatial gradients. So this is not correct. So no, we need to add terms that involve spatial gradients. Because we have a function that is smoothly varying like this. So you would imagine that a function that is flat and a function that is oscillating would have different probabilities of existing. So we want to be able to penalize the strong gradients. We want to penalize strongly varying. Well, actually, let me just not say strongly, rapidly varying functions. Rapidly varying functions M lambda of R. And we want to do that because we know it's a coarse-grained variable. Okay, so we want to suppress those things. So then we can use symmetry. Because in this particular case, we know that the free energy lambda is equal to a scalar. I know that M of R is a scalar. I now want to take lowest order spatial derivatives. Okay, so I want to take low order derivatives. Because I want to suppress rapidly varying functions, and I just want to look at the long wavelengths. So low order derivatives, so then the first thing that you would get would be grad M of R. That would be the first term that you would want to add into the free energy. But this thing is not a scalar. This thing here is a vector. And it has a direction and so on. So then we want to ask, well, what quantity that depends on grad m is a scalar and rotationally invariant. Why should it be rotationally invariant? Well, what we expect is that on large scales, we can't see the crystalline lattice. So therefore, therefore M of R should be rotationally invariant. So we want the lowest order in gradients, spatially rotationally invariant scalar, and the only one that you can construct is this one. This thing is a rotationally invariant scalar that we can add into the free energy. So our approach here is just to say we want a term that is going to be 0 if the system is spatially uniform, but if the system is not spatially uniform, is non-zero, and this term will penalize gradients. So what I propose then is that our m lambda of r has the following form. It looks like this. It's the integral ddr, and then it's going to have the structure like this. Some coefficient, let's call it gamma, times grad m squared, plus a half a m squared, m of r squared, plus 1/4 b of m of r to the 4th, minus h of r m of r. And I don't know why it's oscillating like that, why I have these high frequency oscillations. This then would be the free energy that we would expect. So it has spatial gradients, so that will prohibit it to oscillate too rapidly. So this term over here penalizes departures from spatial uniformity. And that is the way that we can construct our Landau free energy, our effective description, just using symmetry and analyticity. You can also motivate this microscopically from the Ising model Hamiltonian, and that is described in my book. In one of the sections. What the reference is. Okay, so there's an alternative derivation. In section 5.7.6 of my book from the Ising model Hamiltonian. But the main point is that you must, by symmetry, analyticity, phenomenological arguments, it must always end up with something like this. And so next time, I will quickly go through that argument. And then I want to start talking about renormalization group and how we construct a renormalization group theory for phase transitions. Okay, so I'm going to stop there, and I'll be happy to take questions. Let me just turn off Zoom. So I'm stopping the